Hello guys, today I thought we would talk about what makes something a better acid versus a better base. So in this first question, I've highlighted the proton. So if these compounds were to act as acids, then this hydrogen would be removed. We can go over mechanisms in a different video, but for the meantime, the carbon that initially holds this acidic hydrogen, or the atom such as an oxygen, we want to look at its conjugate base, and we always want to argue acidity based on the stability of the conjugate base. So in the conjugate base form, that atom will be negatively charged. So now we must ask, how stable is this negative charge? For example, is it stabilized via resonance or inductive forces? So compound A and compound B, for say, this negative charge, we can create a resonance form, 2 in, 2 up. We could say, oh look, we can move that negative charge from the carbon to the oxygen. So what does this do? This delocalizes the negative charge and it stabilizes the conjugate base. We can also perform resonance in the other direction. 2 in, 2 up. And we get a very similar compound, but on the other side. So overall, this negative charge is delocalized over this entire region. So let's look at the other compound. So here we have an O minus. We can go 2 in, 2 up. You can draw a resonance structure, and the minus will change to that oxygen. And then we can also draw another resonance structure. Two in, 2 up. Where the minus will be on that third oxygen. So we can see here that the negative charge was delocalized over this entire region. So overall, this compound would have the more acidic hydrogen because its conjugate base is more stable. And this mostly has to do with the fact that, okay, they both have resonance. Check. 1. Resonance. Check. 2, we're going to look at, let's say, the atom. Okay, well, this one is on an O minus. Here, the atom is a C minus. Or which one can better stabilize a minus charge? Well, the oxygen can. So better inductive forces there. And we also have the R group, benzene, is arguably more electron withdrawing. So overall, this conjugate base increased the stability of the conjugate base. This is going to increase the acidity, aka decrease the pKa. Now let's look at what makes something a better base. So if we had to look at an imidazole and an azide and ask which compound is a better base, this time we are not going to look at the stability of the conjugate base, but we're going to look at which compound has a more reactive set of unbonded electrons. So this could be a lone pair or a pi bond, for example. Here we have an imidazole, and there's an N that I've highlighted in blue saying, consider this nitrogen, and it has a lone pair on it. Here, both of these nitrogens are going to have 2 lone pairs. So in comparison, the blue nitrogen on the azide or this nitrogen on the imidazole, which lone pair is more readily available to go and attack something? Because at the end of the day, a base is just a nucleophile, but it is a big one, so it's probably going to go attack a hydrogen, for say, but to be a nucleophile, you still need that set of unbonded electrons. So the imidazole, we could say, okay, well, is it delocalized? Because if it's delocalized over a larger region, that's going to be more stable, hence less reactive. Well, here, this lone pair actually, if you look at it, is not involved in the resonance of the ring. because here we could go 2 in, 2 up, draw a resonance form. Minus, and then go 2 in, 2 up. Plus, minus. And we can see that, okay, well, one of these lone pairs, let's make it pink, is there the entire time. So it is actually not being delocalized. It is just fully residing on this nitrogen. So if a H plus came nearby, who's a better base? A C minus or an N with a lone pair? It's arguable, but this is a neutral by form, and I was asking about the nitrogen. So we say, okay, this lone pair is readily available to go bada bing, 2 in, grab that H, and protonate. Whereas here on the A side, you could technically draw a resonance structure and go 2 in, 2 up. This would not be ideal, but technically we could do this. And we could do this with the other lone pair. So we can say, well, both of these lone pairs can technically be delocalized over this region. Hence, this would be increase the stability, decrease the reactivity. You're going to decrease the basicity overall. Another thing we can look at for stability is the orbital. So here we have an sp1, p2, versus here we have an sp1, p2. Oh, well, they're the same. Hence, we can't really look at that. Before we looked at the atom, okay, well, they're both nitrogens, so we can't really look at that. So here we were really just looking at which lone pair is more readily available to go act as a base and grab a hydrogen, and which one is more reactive. Hence, which one is just fully residing on the atom of interest. And the nitrogen in the imidazole would have a lone pair that is fully residing on itself. Hence, it is a better base. We could also look at this question for say and say which is the better base. Okay, well, which lone pair is more reactive? Here we have a lone pair on a carbon, and we have a CN group versus an NO2 group. Which group is more electron withdrawing? You could ask for say. Well, the NO2 group is way more E minus withdrawing. So hence, this negative charge is more stable because it's delocalized by this group that is very near, very close to it. So this would decrease the reactivity, decrease the basicity. Hence, this compound is a better base. There's many more ways to go about answering these types of questions, but this is just the way I've always liked to think of it. It makes the most sense to me looking at which lone pair or which negative charge is going to be the most reactive.